Today's presentation is an introduction to the AccuSizer APS single particle optical sizing system. These basic light obscuration sensors have been around for many years, and that's what we're looking at on this slide. So as a particle passes through a light source, it obscures or blocks some of the light. We call it light obscuration or light extinction. That creates a pulse. The pulse is then interpreted by a pulse height analyzer or the counter, and through the use of a calibration curve, each particle creates a single result in the particle size distribution, and we build that distribution one at a time. Since we build this distribution one at a time, it's a very high resolution, high accurate technique. That is the very basics of light obscuration sensors. But a major advancement that was introduced and patented by particle sizing systems was here you see a sensor where we have two detectors. There's the extinction detector and now a scattering sensor. The extinction detector is used for covering basically the larger size range. As you look at the calibration curve here, let's say from a micron or so above. But as we get below 1 micron, we start getting less of a signal from the extinction detector. So we added a scattering detector. As we get to smaller sizes, we get more of a signal from the scattering detector. We take these two detectors, compress and sum these two different pulses into a single summation pulse. And then that's what's fed into the pulse height analyzer, and with an extended calibration curve, we again, one at a time, build up the results based on, as single particles pass through the light source, the interaction of the particles with that light. You see here the basic dimensions of the flow cell and of the laser beam. So this is the basic principle of the sensor that is used inside the AccuSizer APS system. This is the LE400 sensor. The LE400 sensor combines light extinction, LE, and light scattering, LS. It has a dynamic range of 0.5 to 400 microns and an upper concentration limit of 9,000 particles per ml. This upper concentration limit is important because what we need to do is avoid coincidence. In this lower left hand, you see a single particle passing through the light beam, and here we get a very accurate representation of the size of that particle. But as you look over here at the right where there are two particles at the same time passing through the laser beam, there we're going to size those two particles as a single larger particle, and we call that error a coincidence error. So there's always an upper concentration limit for these sensors, and for the LE400 sensor that's 9,000 particles per ml. So what we need to do for more concentrated samples is dilute the sample to always keep the concentration below that level. Here you just see the extended calibration curve for which is a combination of light extinction and light scattering for the LE400 sensor. This combination of light extinction and light scattering combines high resolution and accuracy with a very broad dynamic range. This is actually a mixture of 11 different polystyrene latex standards going from 0.7 up to 200 microns. Here it's actually on a counts basis, the number of particles counted at each of these size ranges, and it isn't so easy to see the larger sizes here. But in the next slide, when we convert this from a number distribution to a volume distribution, then it's easier to see the contribution from the larger sizes. So just pointing out the very broad dynamic range and high resolution capability of the AccuSizer APS or any of the AccuSizer series of instruments. Now we mentioned we need to get the concentration of the sample down below the concentration limit of the sensor. And in order to do that, we need to dilute the sensor. The AccuSizer APS is actually a two-dilution system, and what this is going to do is aspirate some sample into a sample loop. We'll dilute it once in a chamber and then secondly through another static mixer. This is the Fluidics that allows us to take the very concentrated sample and then deliver it to the sensor at the proper concentration to get the most accurate results. Let's look at the Fluidics here, which is used to automatically dilute the sample. The sample is going to enter here. We'll aspirate the sample, and what we do is we bring it into a sample loop so that we very carefully define the sample volume. From the sample loop, it is then transferred into a dilution chamber. So the loop has volume VL, and the dilution chamber has a volume V1. We can vary these. With this VL could be anywhere from 1 or even like 0.5 mLs up to 5 ml. And we can vary the volume here, but typically let's say if this is VL is 1 and then if V1 is 30, you see a 30-to-1 dilution here in the pre-dilution chamber. And then what we're going to do is transfer the sample from here, and before it enters the sensor, we add another line of filtered diluent, FD. So you have F1 and FD, we combine these, and then this is what's going to be introduced to the sensor for performing the measurement. Let's take a somewhat closer look into the two steps of the dilution. Here we're going to concentrate on F1. So we have the sample which is brought into the sample loop, VL, and then the syringe is going to push that sample over here into the dilution chamber. In this first stage of dilution, DF1 is V1, the volume of the chamber, divided by VL, the volume of the loop. Let's look now at the second stage of dilution, which is where we come up with DF2. So DF1 was defined as V1 over VL. And now what we're going to do is we're going to use a syringe to transfer the sample from the chamber down into the second stage diluter, the static mixture. And that flow rate is F1. The flow rate coming here, this is filtered diluent. It's always filtered because we want to make sure the particles we're measuring are coming from the sample, not from the diluent. So the filtered diluent flow is FD. And we're going to define DF2 as FD divided by F1. And what we can do is we can alter DF2 by varying F1 by varying the flow rate as controlled by the syringe pump you see here. Because what we want to do is have a constant flow rate through the sensor at the proper concentration to avoid any coincidence error from multiple particles in the sensor at the same time. So two-stage dilution with DF1 and DF2. Here we're looking at the dialog box to set up the experiment. We set up the data collection time, the number of channels. We could actually collect up to 512 size channels for a very high resolution, high accurate result. We're controlling the diluent flow rate. The target concentration, the upper concentration limit of the LE400 is 9,000 particles per mil, or we may lower this just to reduce the chance of any coincidence error. Here we enter the value of the loop volume, which could vary from 0.5 up to 5 ml. What's the syringe volume? And what we can do to set DF2 is several things. We could have an automatic step by the system to choose the best value of DF2. If we click on New Sample here, then what it'll do is start at a very high DF2 and then reduce that until it finds the proper concentration for doing the best measurement. Or we could set the second stage dilution factor here if we already know something about the sample. We want to actually control this tightly to make sure that we're measuring this the same way every time. So here we've set up the experiment. All we have to do now is press go and let the instrument perform the automatic measurement. What I'm going to show here is a video performing the measurement. So this sample is actually a lipid emulsion. And you see here we're aspirating the sample up into the loop here. We can pull the tube out of the sample bottle. Although it's sitting there, it's no longer in the sample bottle. And the first thing we do is we check the background. So we're checking the concentration of just the diluent, and we're going to flow that until we reach a very low count rate that we've set to be the expectation for the background count. You see the syringe moving down here, and what we're going to do now is start transferring the sample from the sample loop into the dilution chamber here. And so now as you see that rising up, as you look here, you'll see the sample entering into the mixed chamber. So this is the dilution chamber. Depending on the volume in the loop, it may take multiple pulls of the syringe pump to transfer the sample from the loop into the sample chamber. Here you see it taking a second push-pull of the syringe to completely transfer all the sample from the loop into the dilution chamber. We may then allow a certain period of time, residence time in here, so that we have the well-mixed sample before we start actually measuring the sample. And now the syringe comes down and it's going to push very slowly and very incrementally start increasing the flow rate until we find the correct DF2 value. And once we start analyzing at the correct DF2 value, then we'll actually start the measurement. And on the screen here in a few seconds, you'll actually see the beginning of the analysis of the measurement, and then it'll measure for as long as we've set up. So there you see starting to collect the data. The next thing that happens is we generate a result. And let's look at some example results. The first results we're going to look at will come from ink. These are usually inks for inkjet printers. This is a particle counter. It does give you particle concentration in particles per mil. It also can just be used as a particle size analyzer. In the upper graph, you just see the size distribution of ink as it goes through a grinding process to reduce the particle size to achieve the proper particle size distribution. A few large particles could cause trouble both with the quality of the print, but also could block the pour, which is transferring the ink from the inkjet onto the paper. So we want to remove all large particles. And one of the real strengths of the AccuSizer is to be able to detect a few large particles. So here we see the decrease in particle size distribution, as this is an alumina powder being used for metallic ink as analyzed on the AccuSizer APS. In the right here you see a result for an ink where it's still going through the size reduction steps, but see this tail of large particles? These tails is what could cause the problems, both with the quality of the print and also clogging the pore of the inkjet. So this has still not been reduced to the proper size. In the lower left, you see we now have achieved the particle size distribution with essentially no particles larger than 10 microns. And that's the true strength of the AccuSizer series of instruments and the APS for high concentration samples, this ability to detect tails of distribution. The next result we see here is actually just for the Magenta ink used in an inkjet printer. And here we see the size distribution reduction as a function of dispersion time, going from 50 up to 90 minutes. You see here the total particle count, larger than 1 micron. And we can see the reduction in both tails and in the general size and concentration of particles as we go through this dispersion process. Another very common utilization of the AccuSizer APS is performing particle size and concentration tests on lipid emulsions. If you're familiar with the USP test 729, these are for lipid emulsions that are used to feed patients who need to receive nutrients through an IV drip. In the USP 729 procedure, there are 2 steps, 2 methods. Method 1, which uses dynamic light scattering, like the NICOMP or laser diffraction, is used just to report the mean size of the lipid emulsion. So this gives you a size but not concentration. And the specification for lipid emulsions for method 1 is the mean size must be below 0.5 microns in a certain chi-square, which tells you something about the breadth of the distribution. And here's a result from the NICOMP doing the method 1 test for USP 729. But then method 2 says we want to look at the percent on a volume basis of the droplets larger than 5 microns, which we call a PFAT5. And the industry standard for doing this method 2 test is the AccuSizer. In these photomicrographs, we can easily visualize the difference in these emulsion droplets. On the right-hand side, see these large droplets? The presence of a few large droplets is a very strong indicator that the emulsion is becoming destabilized. Whereas on the left, we see very few large particles, and this is saying this is still a very stable emulsion and safe for the patient. So this is a way to very easily visualize a difference between an emulsion that is still stable and one that is starting to become unstable and could be not safe to give to a patient. But for quantitative and reproducible analysis of the number of particles larger than 5 microns, we need a technique like the AccuSizer. So here's an AccuSizer result for a lipid emulsion where we spiked the emulsion with some 10 micron PSL. This is showing the strength of the AccuSizer to detect the presence of a few large particles. Here we see a spiked sample just to prove the ability to find a few of these large particles. But for the actual test, what we see on this slide are 4 results tracking an emulsion which is destabilizing with time. So in the upper left, we see as you look at the percentage greater than 5 microns, not so much. But then with time, as you see this tail on the large size increasing, then this is probably getting to the point where this is destabilized and would not be safe to give to a patient. So these are the kind of results easily generated using the AccuSizer APS to look at the percent of particles greater than 5 microns. There is also, when you do USP 729, a requirement for the repeatability of these measurements. And what we see here are 5 different samples analyzed using the AccuSizer APS. And these results in terms of the percent of particles greater than 5 microns must be within 5%. And we see that very easily achieved using the AccuSizer APS. So what we have here is a combination of wide dynamic range, high accuracy, high sensitivity, the best sensitivity to be able to detect a few large particles. We actually have other studies documented on our download center which could prove the ability of the AccuSizer to detect these large particles as being more than 600 times more sensitive than a technique of laser diffraction. But that's what I wanted to cover today. Quick introduction to the AccuSizer APS, which is a liquid particle counter but also a high-resolution particle size analyzer. It is the technique with the best sensitivity to tails of distributions, either large tails as we discussed here today or on the smaller side. It has the most advanced auto-dilution capabilities. We have discussed the 2-stage dilution system built into the APS, which allows us to take very concentrated samples, but then make very accurate measurements with no coincidence error. If we're working in an environment where we have many samples to analyze, a high sample load, then we have auto samplers, which can help with that. And if you'd like additional information on the AccuSizer APS, I do recommend you visit the documentation download on the website. I give the URL here. And there you could download additional notes, for instance, on USP 729 or on measuring inks or on other applications where you could see how the AccuSizer APS has been utilized to take very repeatable, excellent measurements over a wide range of samples.